Hello, I think we're on episode 12. Welcome to that, then, if it is episode 12. Whew, okay, I want to look at this. I'm convinced that this might be a bug, because it makes sense to me that there are two of these, because I knew that when I was building the operator parser that it was going to automatically insert a fallback on every single transition rule, just because you need every transition rule needs to know how to handle every situation. And I was thinking to myself, well, there will be cases where I haven't inserted a fallback yet that will catch everything. So, in any case where I haven't inserted a fallback yet, this will just make sure that there is a fallback, and then the optimizer will find that and remove it. But what doesn't make so much sense is that there are fallbacks before actual character things, because that would mean that it inserted a fallback before it was actually necessarily done inserting special behaviors. So this emit here is actually unreachable, but it seems likely that that emit contains useful information. In fact, this seems like someone was had already consumed one left arrow or one greater than sign, and if they saw this, they were going to call it a right shift operator and go to a state that either would finish parsing a right shift operator, or turn it into like a right shift equals situation, or turn it into a greater than or equal to situation, right? It seems like that's what this is about, yet someone ended up putting a fallback in between, which means this will never be relevant. That's kind of what it feels like is happening here. For instance, what is this? Why are there so many fallbacks in a row here? I'm convinced that something fishy is happening here. So, we're going to go to the piece of code here that actually builds, whoa, zoom in a little bit for you, that actually builds a Lexer state machine from an operator set, and we're going to walk through it and see what it looks like. Not relevant. Relevant. Okay. So the first thing we do is we create a new root. I'm going to stick this here. So this root is the root of the operator parser. It's the thing we're going to return here. And it essentially is just the handle to the generated state machine that is going to be included into the rest of the state machine by just saying transition to that root, and then that root will dispatch you to the rest of the state machine correctly. There's also, you'll notice, I pass in the machine root so that when this Lexer parser finishes its job, it goes back to the root that was external to this system. So this entire system is built as sort of a set of states that finds out what operator you're at, and then once it's got an operator, it emits it and goes back to the machine root that you provided, and then it returns an entry point into this sort of, essentially like maybe you could think of it as a function or a reusable procedure, or just a cluster of states that are generated together as a sort of special situation, right? They're kind of isolated from everyone else by this, by the fact that they're not constructed side by side with them. They only connect to each other. Things outside of here can only connect to this, with the exception that all of these can connect back to the main root, and anything out there can connect to this, right? So that's how there's like these choke points where everything can reflow back to each other, but this is sort of isolates the job of making an operator parser. And the other thing is it automates it by taking in an operator set that's just a list of operators and figuring out how to output the correct state machine for parsing that set of operators using a maximum munch rule. So, in other words, it's going to use the rule that C++ uses that says if there are two possible operators that both start with the same thing, I'm going to always assume that if I could make a longer operator that I should, but I'll take the shortest operator. I'll take the longest, basically I'll take the longest valid operator I can get starting here, is essentially the best way to put it, I guess. And if it turns out, like, there's some weird cases where it's like, what if there's an intermediate where it's like, the length of this thing is longer than, is not long enough to be this particular operator, but it's too long to be anything else, so it's like in an in-between state where it's not valid, but we consumed it because it could have been, like, if we see 2 periods but not 3, so it's 2 periods and then something else, there's kind of an ambiguity there in terms of, I mean, it could be 2 period operators, right, 2 period lexemes in a row, which might be the correct way to interpret the maximum munch rule, but that's never a valid construction in C++ anyway, so I just treat that as a Lexer error if it sees 2 periods in a row and not a third one. right? So if it has like an intermediate that does not get resolved by the first two rules, the third rule is it's always an error. The first two rules are if you can consume the next character to make a longer operator, do so and keep trying to find a longer operator. If you can't, then emit the operator you've got so far. If you don't have an operator so far, then you emit an error. That's the third rule, right? Got it? So we make a new root. Then what we're going to do is I want to look at, when we're iterating here, we're looking through these operators. So for each operator we have an op, which is the name of the lexeme of the operator, and then separately the name. We're essentially ignoring the name for now and just taking the lexeme. And then we're going to say how long is this thing, well not how long is it, but iterate its substring. So this has no prefixes. Iterate its prefixes. This has no prefixes because it's only length 1, so nothing happens. Now why are we iterating the prefixes? Well, the idea is that for each prefix we find, once we find one I'll walk through it and explain it while we do. No. Here we go. For each prefix we find, what do? Well, we take that prefix string and we look up in the table to see if that prefix already has been visited once before. So in this case, this is the first prefix, so we have not got a copy of this. We do not have a thing for this prefix yet. So what we do with a prefix when we find it is we add it to the state machine by making a new state for that particular prefix. So we have a new state that represents having consumed 1 colon now, and we figure out what the parent to that should be. If our prefix has a length of 1, then the parent is the root. It's a first level prefix. It's a prefix of length 1, so we transition to this state from root. So the parent is called root in this case. Then what we do is we look at what character this prefix is made up of. So space is just the space where we contain that character, and it's a colon, right? And then we say, okay, so our character array here is a colon, and it's 1 right there, and then we say, make a transition case. So we add a transition case to the state we just made that says, or to the parent of the state we just made that says, when you're at parent, if you see this input, go to this state. So now it is set up that when you're at root, if you see a colon, you go to the state we just made. Finally, we save the state we just made into this table so that next time someone comes with a colon prefix, we will find it. That's all the prefixes for that operator. Moving on, we find plus plus. Again, that doesn't exist yet. We're going to put on parent that if you see a plus, you transition to this state we just made, and now we save that we found that. Minus minus is going to do the same thing again. So we're now just finding all of these prefixes. Minus already has been in the table, so this should be a 1, and we do nothing. Okay? We're looking for operators that are longer than 1 character. Here's another one. We already have dash, so this will do nothing. But do we have dash arrow? So this is a lexeme of length 2 now, a prefix of length 2. We look that up, and no, we don't have any such thing. So now, this does not happen. We say, okay, what is the previous? Well, the previous is we take this prefix and we subtract 1 character off it. So what's 1 prefix shorter than this, right? In this case, a prefix 1 shorter than this is the subtraction operator. So we should successfully find that because we've already inserted it. And you'll notice that we're always guaranteed to have inserted the previous prefix because we do them in order from shortest to longest when we're doing this. So even if dash hadn't been in there yet, or the subtract hadn't been in there yet, it would get put in before this stage. So we can assert that we're always supposed to find that previous prefix. We read it, and we get a parent pointer. So now we have a parent that should be different from root, 304968, and our root is 304678. So they are different. So we have this parent, and now we say whenever you see, and what do we ask for now? Well, it's not the first character, it's the second character. So space should be an arrow sign, and it is. Whenever you're in the state where you've seen a dash and you then see a right arrow, we'll then transition to something where you've seen a dash and a right arrow, and that's the state we just created. Store this new state we just created as the pointer or the state associated to the prefix that we are on, which is dash arrow. Right, and continue. Right, so I think that that looks like it's doing something reasonable that I can understand, and that seems like it's coherent. It's doing, it makes sense. So all the prefixes end up as these state things here, and the only case handler we're adding to any of these states is that these single character things. So that all seems reasonable, and I'm happy with that structure. Next, we look through all the operators again. So this was a first pass over the operators. During the second pass over the operators, what I'm doing is I'm saying, okay, look at your lexeme and look to see if you're already in the table. So is open brace already in the table? Remember, prefixes, only prefixes got inserted here, so you're not necessarily guaranteed to be in the table. If you're a single length operator and you're not the prefix to any other operator, then you won't be in the table. And that's the case here. Is the open curly brace is not in the table. So it's going to again figure out the root for this thing should be root, or the parent for this thing should be root, and now it's going to emit a case that says character array. If you see, so now we're looking at the last character of the full lexeme. In this case, the last character of the full lexeme is just a curly brace. If you see a curly brace, we're saying, then you should do an emit handler, and here's the transition case for that. So you're doing an emit. The emit you're doing is for this particular type of token, so a brace op, and the the transition rule is that one character there if we see that when we're at the parent, where in this case the parent is the root. So now we're adding again singular character case handlers to a parent node, and that seems fine. So I think I see where things are going to go wrong. Here we're adding singulars, but what happens when we finally reach this stage? Well, what happens here is we're seeing, for instance, okay, colon. Colon is not going to go into the colon case and say, all right, if we've got a thing that says if you consume a colon, then we have a special state for that. So now what we are doing is we're saying, okay, if that state already exists, then we can't insert a case handler into its parent because the thing for that state already exists. There's already something happening when we see a single colon. So instead what we're doing is we're saying, okay, if you ever see anything that doesn't, like if you're seeing fallback basically, no matter what you see next, finish it by emitting a colon. I think that's wrong because later we might end up seeing colon colon. Here it is, colon colon, and now colon colon is going to go and emit a single here. So the problem that is arising here is that these singles are being emitted after these fallbacks, right? And that isn't correct, and the reason it's happening is because I try to do this all in one pass, saying, hey, look up to see if your state exists, and for the full lexeme. And if the full lexeme state does not exist, then I create one of these. Now this can't be the same as this code up here because this doesn't do emits. This is always interstate, like if it's a prefix, it's always an intermediate state, whereas here it should be a final state that actually emits and transitions back to the machine root. So that's different from this. But it's also not creating a new state, you'll see, right? This is transitions to machine root, whereas this creates a new state. This doesn't emit. This does not do an emit. They're very different. But these are also very different and actually can't be applied until after all of these have been applied. So this needs to get split into two loops and then reordered so that all of these handles or situations happen after all of these. Is this going to create a problem, though? The way I tell whether or not to do this or not is whether or not this thing already exists here. So anything that would have hit this case still will, but will I start hitting cases once I've done this? The answer is should be no, because I'm not doing any table inserts here. So this doesn't change the table at all, which means that I can still count on this to give me the same result on a second loop. Okay, let's make that rearrangement and see if the resulting state or operator parser looks any different, right? So that's under main 1807. Yeah, we want to take this entire loop and duplicate it, and then what we want to say is this section does not ever happen here. So if we look something up in the table and we don't find a match for it, then we poke in a single character handler that transitions that character to an emit end to the machine root, right? So we see that character and we say, all right, we can now say we consume that character and we emit a token, and we know there is no way to continue this token any farther than this. This is as long as the token gets, so we emit it now and be done, right? Don't even need to, like, leave room for whatever comes next. Whatever comes next is irrelevant. This is the final token. On the other hand, if we are in this situation, then the state, the full lexeme for this particular operator happens to be the prefix for someone else, right? Someone else has inserted into the table, into the prefix state table, basically, the table of all the lexeme prefixes, a state pointer, and said, this is the state we reach when we've seen this prefix. And that prefix also happens to be a full token. So when we are iterating, we find that situation, then what we want to do is say, okay, so you're a full token, but the lexeme for the full token already exists in the system as an interstitial state, which means that there is a way to continue this operator. If we've seen, for instance, a single colon, there's a way to continue that operator, and we have to wait till we see the next character to know for sure that we're done. But if what we consume isn't any of the things that create a continuation, then that means it wasn't added here and it wasn't added here. Then we can go ahead and say, then in that case, anything else that we see does in fact lead to emitting U, right? So if the next thing we see continues is another interstitial thing, like if you're a minus sign and the next thing we see is an arrow, then the case handler for that will have been inserted here. If you're a minus sign and the next thing we see is a minus sign, then this is the case handler where that case handler got inserted. So we'll immediately emit a minus token and go back to root, or to the machine root, right? If neither of those things happen, then, and it's not an equal sign either, right? If the next thing we see doesn't continue any tokens, any of the things that we've already emitted, then you are a minus sign, and we'll emit the minus sign that you say, like the name of the token that you say you are, and then go back to the machine root in that case, and we'll do that as a fallback because it doesn't matter what we saw. But we're doing this with a no consume rule because unlike the previous ones, we don't actually want to think about in this situation what happens when we see whatever character triggered this. Whatever character triggered this might be the beginning of an identifier, it might be the beginning of an integer, it might be the beginning of white space, it might be another operator. It's not we don't want it to be on us now to write out all the rules about what happens, so we don't consume this. We let the machine root figure out what to do next, because it's sort of the thing that starts new tokens. Alright, once we've done all that, the last thing we do here is we, let's see, string, fallback, why is there a string at all? I don't get why there's a string. Oh, that's just a zero string for that. Okay, should name that 0 so that I know it's intentionally zeroed and not getting set to anything. So the 0 string is just a parameter that's getting ignored, but we're saying emit a fallback onto our root. So everything else here has got a fallback. These are fallbacks that actually produce useful tokens. Now what we're going to do is say, okay, anything else that happens, if we haven't already found a token, so there are some states that, like I said, we thought we were trying to parse an operator, but we saw some character we don't know how to handle, or we saw 2 dots, but the third dot didn't materialize, so token dot didn't get a fallback here, and it didn't get a specific handler here. So now what we do is we say, alright, if none of these have triggered yet, there's a final fallback. We add it to every possible state. We don't think about whether or not to add it. We don't think, did you already get a fallback or not? That's too much work. We just put it in there and say that'll get optimized out if it's completely eclipsed by a different fallback or by a different set of operators altogether, like handlers altogether. But every state in the system, including the root we've generated and all of the states afterwards, get a no consume fallback that just says emit the fallback type, right? And some of those will get eliminated by the transition simplifier and others won't, and the ones that don't, that's the reason we're adding them there, so that everybody is guaranteed to have at least a final fallback to give us the fallback token name, which will be Lexer error in most cases. Okay? So I think that was the only bug, was that we needed to split this into 2 loops when it was actually 1. So now we're doing 3 passes and then of major computation plus 1 more pass to do the the thing here. And you'll notice that what this is actually doing is generating a bunch of extra fallbacks. So this is looking at every node. For each node, it's looking at the lexeme, and it's looking at all of the prefixes for that lexeme, and saying, put a fallback on there. And that's why we ended up with like so many fallbacks on this one, for instance. This must be somebody who is they're the prefix to a lot of tokens, right? So what we could do to not have so much of this, well, this is already getting optimized out anyway, but if we really were pissed that we had so much and we wanted it to go away, what we could do instead is say, why aren't we just keeping a list of the states we generate in this process, or iterating the string table right here, right? We have a string table, maybe we can visit everything in the string table once instead of trying to do this. Here's the thing, is no matter what I do, I have to write new code, and this code I think is already going to work, so it wins. So now, we'll still see weird long chains of 257s in here at places, but I don't think we're going to see any of the fallbacks happening before specific character handlers now, which makes a lot more sense. Okay? And then, if we go ahead and let the simplifications happen before we print this out, I should really do this way. If we let the simplifications happen before we print anything out, then when we come down here, these will say 256. There will be no things where there's like 257s multiple times in a row, and there we go. So our input, our transition simplifier is taking care of the redundant fallbacks, and the machine, or the operator state machine generator, the thing that generates a state machine for operator parsing, is now correct. So we aren't getting any weird things where we have characters getting eclipsed by fallbacks that got inserted erroneously before them. And now that we've done that, I want to see if that changes. Earlier it looked like there were a lot of things in a row here that were just fallbacks with nothing to do, but now when I look at it, I'm actually seeing that the story is different. Now what we have is a lot of situations where there's like a single character that does something useful and everybody else does something, everything else is caught by a fallback. So like a lot of these look like these are assignment operators getting finished, or possibly the comparison operators getting finished too. Right? We still have a lot of places where we have like a fallback that does no consume, but it does like fallback, emit, go to root. So we probably want to think about how we're going to optimize situations where there's an emit, go to root with no consume, right? If there's not a consume first, but there's a go to root, then we want to pull forward everything that the root has. But if we do that way, what's going to happen is each one of these is going to turn into something almost as complicated as the root itself, because 256 of the possible inputs will still apply. And the only difference is for every possible transition that the root had, there will be an emit first, and then all of that. And then there will be this one will be different. These won't be able to collapse into the same behavior because this is emitting something different than this, right? So it does kind of make you wonder what's the move going to be there to prevent that go to root from expanding out to being gigantic. And probably the answer is, if we are doing this as a control flow generated system, we wouldn't actually want to apply that indiscriminately, pulling everything forward if the thing we're pulling forward is too big. If the thing we're pulling forward is small, we would do it, but if it's huge, like the root, we would probably leave it in so that we can just use it as a jump. On the other hand, if we're doing lookup table accelerators, and the lookup table and we like find a good way to do the isolations and stuff so we can have nice small tables, then we don't really care how many cases there are under anything, because everything has to have its full breadth of cases defined anyway, and we would actually be benefited by always consuming, because then we don't need a special table for determining whether or not we consume. So which optimization we apply to the structure next is determined a lot by what output we want to make. But I kind of think that there are some other optimizations we can apply that are simpler that we should do first, that will be universal, that will apply in both cases. And that's getting rid of these thunk states, right? So we can get rid of thunk states, and that'll help in both cases. Then what we maybe want to do is we want to think about if we actually know how to isolate so that we can do lookup table acceleration. And if we can find a good way to do isolation of the state machine into sub-state machines that makes it possible to minimize the size of our lookup tables, then we'll go ahead and apply this, right? So this is if using lookup tables do this optimization. If we don't think we can find a good way to do this, then we won't apply this optimization or write the code for it, and instead we will go down this path here. So that's going to be a kind of, out of order. We're going to have to think about one step at a time which things we do and don't think we can achieve. But let's see if we can optimize out all the thunk states in this rest of this episode, because I don't think that's that complicated. So what's a thunk state? A thunk state is anything that always does the same thing on its input and does not consume. So if I had a state that always does the same thing but it consumes that character, then I might be able to find a way to optimize that out, but I'm not sure. It's a little hard to say. Like, if all you do is consume a character and then go to someone else, then I still think I could pull that forward, right? Because you're basically saying you're throwing the character away. Because if you consume something and then you don't do something like set flag afterwards or something, then it means, well, basically if you consume no matter what you see, you consume it, then you don't need to check what it is before you do the consume. So then you can actually feel free to pull that consume forward, and that's kind of the point, I think. This does the same thing no matter what it sees, so this might as well be just removed, and wherever someone entered into it, have them do whatever this was going to do, right? So basically what we want to do is look through all the states, and if any state has one input handler that looks like this, then we are going to mark it as like needing to be optimized out. Then what we're going to do is walk through all of the states again, and anyone who has a transition into someone who needs to get optimized out, we'll just pull forward their transition list and their destination state into their own case handler, right? Finally, we will say all those ones that needed to get optimized out, just take them out of the list of existing states. And so hopefully, after this optimization, we'll see the number of states go down a little bit, which will be cool. It'll be cool. It'll be fun. So what we're going to do here is we're going to say opt something like we want to unmark all thunk states. And then we want to, well, I guess what I really want to do is just skip past thunk states, and then do this again to optimize out the states that no longer need to exist. And then finally do this again to see how the new thing looks compared to the old thing, right? So, how do we implement opt skip past thunk states? That's the only question we have to answer. How do you skip past a thunk state? Okay. So first, we need to say, let's make sure everything is still marked as included. So unmark, where is the thing that, okay, mark all states included. So this marks all of the states we have as included. That's the first thing we want to do. Then what we want to do is we want to loop over our states, and we want to figure out if a state we're looking at is a thunk state. So again, a thunk state is one where there is one transition, so that'll be the first test. State transitions. Now technically, if our system type checks correctly, and it has one transition, there's a rule that all possible conditions must be handled, right? Transitions.count equals 1. So if all possible conditions must be handled and I only have one transition, then that condition, the condition on that transition must be like a do everything transition, right? It must be a transition that catches all possible conditions, right? So if we have one transition, we're a thunk state, and what we're going to do for any thunk state is we're going to say that you are not optimized in anymore. So here we marked them all as included, then we said you're no longer optimized in. Next move is we're going to loop through all the states again, and we're going to say anyone who's looking, whoops, loop through all the states again. This time what we're doing is a loop over transitions, So loop over transitions looks like this. We're looking at all the transitions, and first of all, what we're going to do is we're going to say if the state we are looking at is optimized in. We're going to not bother to do this to states that we're about to remove anyway. We don't want to alter them. But any state that is still included because it isn't a thunk state is now going to let's see. By the way, we could do right here more creative thunk state tests. A more complete thunk state test would check if all states have the same effect. If all transitions have the same effect. If they do, then it is a thunk state. Only having one transition is just a special case of all of this more general rule. Okay. So, skip past all thunk states, check if it's a thunk state, optimize it out. For each transition, what do we do? For each transition, what do we do? What am I missing here? I'm not thinking something through clearly. Transitions. Oh, for each transition, if the transition's dest state is not optimized in, then what we want to do is a pull forward mechanic. So basically we're going to say we're looking at somebody who says they're not optimized in anymore, right? And that's only possible if they didn't pass this, check here to see if they're a thunk state. So we must be looking at transitioning into a thunk state. Since it's a thunk state, what we can do is just grab the first transition out of that destination. So we're going to say this transition transitions to a dest state, and that destination state has a set of transitions, and that set of transitions has a first transition. That's the destination transition. Now, like up here, we've already tested that like the general test we haven't done yet, but one way or the other, all the transitions are the same, so it doesn't matter which one we grab. We can just grab the first one. Then what we're going to do is say, okay, what we need to do finally is a pull forward mechanism that says whatever this transition says it's going to do in terms of its activation and its destination state, pull that forward into this transition. So this is like opt transition pull behavior forward. Right? So we want to pull forward into, let's see, I'm going to give you the context. I'm going to give you the transition that's going to get the new behaviors and the transition that is getting stuff leached out of it. Now we're not going to delete anything out of this one. We're just reading out of it, and we're going to insert copies of everything it does into here. Then there's another rule, which is once we've done that, what we want to do is say this is actually happening on a loop. So every time we do this, we're leeching something forward. The new destination might also be a thunk, in which case we want to leech it forward again. And so as we're doing this, we can't just we can't just do this by looking through each thunk and finding the last thunk in the chain, because while thunks are possible to optimize out, they might have actions attached to them that need to be preserved. So we need to go through them one by one and pull forward all of their actions too, so that if they're doing things like consuming or emitting tokens, we end up taking those actions on to our own transition, right? So that's why we are going to pull forward the behavior of this transition, and then what we're going to do is loop back around and say, okay, if we're still in a situation where the destination state isn't optimized in, then do this whole thing again. Grab the next destination state, pull it forward, and go again. Now, what if we are doing this and we get into a loop? first of all, is that possible? In order for us to get into a loop, we would have to what? We would have to eventually get to a situation where a thunk state that we have already visited once is once again getting pulled forward into us. So, in other words, we're in a situation where the state machine no longer is ever reading input and is ignoring everything that happens and just doing a cycle over and over again forever. If such a thing existed in the state machine, how would we ever resolve that? How would it get done? Well, it's possible, because it isn't possible that the loop contains the state we started on, because this state is not a thunk, but we could easily just make a thing where there are two thunk states that thunk back and forth to each other for all time, so that once you go into one of them, you just bounce back and forth forever, and we need to know that we've already visited a state if that ever happens, because then what we'll do is we'll say, fine, we've got to a point where we're in a thunk state loop, and we need to figure out a better way to resolve that situation. So how would we resolve a thunk state loop, and how would we detect it? In that order, let's think about it. So to resolve it, what we would need to do is say, first of all, this isn't invalid. This is unusual, but it's not invalid. The state machine, as I've defined it, doesn't have to have an exit state, right? It doesn't need to say that it exits whenever it wants. Rather, it is done when the person putting input in has no more input for it to consume. So, it makes perfect sense to say you might, in a sense, be able to consider the whole thing as eventually a thunk state machine, right? The whole state machine just stays inside of itself, calling other things. In a particular sense, you could say if we reduce, yeah, some of them transition to different states, but does it ever do anything other than transition to a new state and emit tokens and do stuff? No, it doesn't. So really what we're talking about is having a sub-state machine within a state machine that just happens to do the same thing in a cycle. No matter what input it sees, for every character it sees, it does the next thing in a particular cycle, right? So it's like the first character I see, I ignore it. I consume it, but I ignore it, and I do this. I consume the next one without reading it, and I do this. I consume the next one, and I read it without doing this, and then I go back to the beginning. So it creates this little sub-loop that the only way it's different from a state machine is that it is now completely untethered from the input. We could optimize out even having to read the inputs and just look at the number of inputs that we've seen as our only guiding factor from then on, right? So that doesn't quite fit into anything the model can represent so far. Furthermore, if we were going to do that, how would it look, and what would be inside that thing? Essentially what we're talking about is just an action list, right? We're talking about having an action list that can contain things like consumes and stuff. Now, it should be noted that we must have consumes. It isn't valid. It's totally valid to have one of these thunk cycles, because a thunk is just a situation where the same behavior happens no matter what. A peak, or somebody who does not consume their input, same thing as a peak, right? They read the input, or maybe not read the input. They might not discriminate on the input or not, but they don't consume it. If there's ever a cycle of those things, the type checker has to find that first, because that would lead to a situation where an infinite number of things has to happen, and obviously that's against the rules, right? You have to eventually consume every input that you're fed. So we're not talking about a situation where we're getting into an infinite loop. We're talking about a situation where we continuously consume characters, but we kind of need to know, we need to have the concept that there's blocks of these actions, right? So these actions don't just flow freely as a list. There's a little bit more to it than that. Because as states, what happens is whatever state you're in, some actions can happen, like you read the next character, and so the person outside of the state machine who's putting inputs in, puts in an input. The current state decides what it does about that. If we ignore peaks for now, it's going to do it can do some actions, right? It can maybe emit a token, it can maybe do some other more complicated stuff with the delimiter matching, change a flag, based on the input itself. Then it can consume that input eventually, and then it can do some more actions, and then finally it does a transition. Right, so the state machine blocks things up like that. So that block of things all happens together in response to one input of character. Now, the new system we're looking at here, right, essentially whenever there's a block with a consume in it, that one has to be terminal, right? So even if we aren't discriminating on what character we're being given, we still need to know, okay, after a consume, there's two more actions. Those two actions are kind of glued to that consume action. So there's like you put in a character, you do all the actions you can until you find a consume, and then you have to finish that block. Then the next character that comes in may be the same set of actions. Again, it might be a different set of actions. There might be 100 different blocks that each character triggers one of these blocks. And so that's what's actually got to happen. We can ignore the consuming, or rather, when you can't ignore it, we need to keep track of it, the fact that it's kind of happening. But when we fall into one of these sort of like dummy loop things that is non-discriminatory about what input it's given, we now need a sort of action list in chunks, right? So that we can say for each input, you do the next action list. And you never care about what the input is again, you just do the next action list in the cycle, right? So that's how we would handle it, is we need a data structure like that. The next thing we would need to do is say, once we know how to build that thing, we want to say that we can, while we're pulling actions forward, detect that that's happening, and instead of putting all those actions onto the state transition, like basically suppose we see a thunk, 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 and then, oh, there's a thunk cycle, or wherever that thunk cycle repeated back to, whether it was the previous thunk, or the first thunk in that we ever saw, or one of the ones in the middle, we want to cut that off there and say, okay, the transition handler only does the thunks that aren't part of the cycle. Wherever the cycle starts, it transitions to this cycle handler thing. So that's the second thing we've got to think about getting in there correctly. The third thing is, this rule about blocks actually applies even for non-cycle situations now that I think about it more out loudly. So suppose we have a situation where we don't get into a cycle, but we do have a long chain of thunks that does several consumes. Well, each of those consumes is non-discriminatory consume. So it does the concept of, it doesn't matter what the input was, it's doing the same actions, but it does have the idea that like it's consuming that character. So we need to know which set of actions gets associated with each character, so that if we have a state that we're like, okay, we see a character and we discriminate, we're doing a discriminatory check on that, and we say, here's the handler. That handler might go into a situation where now we need to see three characters, and no matter what those three characters are, we're going to do the same thing, right? No matter what we are consuming, we don't care. We consume it, we do a couple other actions, and we're done. But then we don't need to transition to another state, per se, or at least not a major state. What we need to do is remember what the next action, like the next block of actions in the super action list is like. So we have these action lists that are like, here are the actions you want to do, but we want to group those into like, here's the actions you do to one character, and here are the actions you do to the next character. Most states would only ever have one of these blocks because they're doing a discrimination on the character, doing some work, and then going to a different state or to the same state, but whatever state they're going to usually discriminates on what character comes next. But anytime it doesn't discriminate on what character comes next, we pull that block forward and say, okay, so this thing here doesn't discriminate on which action comes next, so we're pulling its block forward, and then we're saying this block does contain a consume, so it's a separate block from the one you already had. You can't merge them into separate blocks, but you don't need to transition to a different state. Rather, you need to know to stop doing this list of actions once you're like, once you have the first character, wait for a character, and no matter what character you get, you do your second list of actions. And there is no transition until all of the blocks are done, right? Or if we're in one of those things where we never transition again, then we just will insert in the idea that these blocks chains, these like, not block chains, forget I said that, these lists of action blocks can have like a cycle in them, right? Like a cyclical rule that says, hey, when you get done when you finish this action block, the next action block is this other action block that already you have in the same chain, right? So that would work. It's a little more high level than what I thought this needed to be, but that's kind of sort of par for the course when you start trying to write these sort of optimizer things, right? So what can we do to simplify the whole situation? Well, one thing we could do is say that we don't want anything that does a consume to be in our action list for now. We could say, let's avoid all this problem with blocking, block stuff, right? So what happens right now is we are pulling these things forward, and we're saying all of these thunks we're pulling forward. What we could do is say there are not going to be any cycles of peaks, so if we say even if you look like a thunk according to this rule, if your behavior in your transition contains a consume, then we're not going to treat you as a thunk for now. A more strong optimization would be treat that as a thunk and do all this action block listing stuff. But instead of going down that road right now today, a lot of the stuff we're trying to optimize out doesn't actually need that. Let me demonstrate what I mean. If we take out the stuff we're trying to add in right now for optimization and just run again, oops, I didn't put in a print. Okay. Put in a print. So a lot of the things that are thunks, let's see, 257, don't do a consume. So that comment block thing doesn't do a consume. This, oh, that's not actually a thunk. That's a delimiter match. That's a different thing. Are those the only two things that qualify according to this rule as a thunk anymore? Or is control being weird again? There it is. Okay. So this wouldn't count as a thunk. Even though it always does the same thing, we're kind of nervous that pulling this consume forward is going to complicate things, so we're not treating that as a thunk. This would still get optimized out, this would 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 get optimized out. So plenty of stuff will get optimized out doing this. There's actually only one thing in here that doesn't get optimized out that could get optimized out by not doing this extra work, right? So for a great deal more work, I could get one more thing out. I'm not going to do that right now. Maybe someday, but I think for now what I want to do is I want to see this go down by like 4 or 5 rather than 6 for like the 20-minute amount of work that I have left in a single episode, and for the simplicity that I get for that, right? If I want to later, or if the state machine the code gets used for lots of situations where having action blocks like I was describing would pay off a lot more, or if I just have some free time and feel like doing some optimization work on this for funsies, which is not actually out of the question, then I'll come in here and do that. But now is not the time, because I think we can get a big enough win from not going all the way down that rabbit hole for now, right? So let's just say that we're not treating you as a thunk, is optimized in. We're not treating you as a thunk if your transition contains a consume, right? So to do that check, let's see what a transition contains in it. It contains an activation actions list. Okay, so action, well, hold on, let me do this the right way. Node act. Alright, we look at activation actions stuff first. Yeah. No. Contains consume equals false. If, as we're looking at these actions, we find an action that does a consume, then we're going to say that it contains a consume, and we'll be done, right? And then if it does not contain a consume, then we say that it's not optimized in. So this right here is going to be to do. If consumes could be pulled forward into the transition handler, transition actions for these types of thunk states as well, but only if we add a new concept for representing action blocks separately from actions contained in a transition handler, so that a handler can have multiple blocks. Then we would need to be able to identify thunk cycles and add an entire extra concept to the state machine generated code that it can sometimes get into a stateless thunk loop that can never be exited, but continues to consume one input at a time, doing each action block. Okay. It's a fairly complicated thought process that we went through to get to that idea. I don't necessarily want to lose the full idea. I hope that that's a good enough explanation for it in case I ever want to come back here and do these kinds of things. But for now, again, the things we're actually seeing in our output don't map to this problem. So I think we're fine just doing this. So now we want to do this pull behavior forward thing. Now pull behavior forward is going to be useful in so many cases that I'm happy to have it as a separate thing. That's why I'm not writing it directly in, because if we ever do want to do something like optimizing out any peak case handlers, we will want to be able to say that we can pull things forward in that situation too, because peaks are just a different way to essentially skip. This is two different logics that allow you to skip through states, right? Thunk states are states that there are no point in transitioning to them, and peaks are transition handler or action lists that don't contain a consume, and therefore could predict what the next state would do by just looking at it and pulling forward its behavior, right? Either way, you're avoiding putting in some extra states. So this is a nice handy thing to have. Now if I ever did add the action blocks thing, this would have to change a little bit, because the idea of pulling things forward would no longer apply to actions but to action blocks, and then I'd need a concept of merging action blocks whenever neighboring action blocks. Like basically what would happen is each transition would initially have one action block in it, and when you pull something forward from another action block, you'd have multiple action blocks, but then you'd have a path that simplifies action blocks by saying if an action block does not contain a consume, it can just merge to the next action block below it, right, and combine their actions into one. An action block doesn't have to be separate until it contains a consume. Once it contains a consume, it can't merge to the next one, because the actions that happen in the next block should not happen until the next input happens. Could we ever have actions with multiple action blocks with multiple consumes in them? I don't actually see any reason why you couldn't, except that no, actually I don't think you could, because it would imply that you know you have two inputs, which you actually don't. Each action block essentially is saying I handle a particular input, and if it doesn't contain a consume, then it's also saying someone else actually needs to handle this input too, and if it does contain a consume, then that's actually just its way of saying once I am done with all my actions, we are done handling this input, and we should get the next one if there is one, or wait forever for the next one if there isn't one. Right? And by wait forever, what I mean is do nothing. Wait for nothing happens at all. Okay. Pull behavior forward. So how does this want to get implemented in the current world? Do I have a way of copying action lists? Because I think I do. Action list copy action list. There it is. So what we're going to do is we're going to make a copy of the action list. So this is sort of like, okay, when I'm pulling behavior forward, this is going to be the skipped transition, and this is going to be the initial transition or something like that, right? Abbreviate transition. There we go. Okay, so action list I want to copy is going to be the skipped actions, and this is only going to happen ever if the skipped transition list actually has any activation list at all. So if that does anything, we are going to let's see, opt copy action list. Here's the arena on which that goes, and here is the action list to copy, right? And then what we want to do is concatenate that onto the action list of the initial transition. So that'll just go, okay, if the initial transition first equals 0, initial transition activation actions first equals 0, then the initial transition activation actions can just equal this new copy that we made, right? Else, if, well, we're kind of assuming that we're not having a 0 situation, so otherwise, this guy's last becomes the skipped actions first. This guy's last next, I mean. This guy's last becomes the skipped actions last, and this guy's count goes up by the skipped actions count. Alright? So that pulled forward all the actions. Then the only other thing we have to do is whether or not there were actions. A transition always contains a single destination state, and so the initial transition state needs to, or the transition needs to pull forward the information about what transition or what state to transition to, because we're skipping over this state entirely. So, or this transition entirely. So this transition, we're basically saying we know that this transition leads to this transition. So just augment this transition to have everything that this transition does, and that includes transitioning to the correct state after everything else, right? So now, there we go. So this dropped to 74, and I believe it was 76 initially, right? Yeah. So I kind of want to look at that and figure out why it only dropped by 2, because I would have thought there were more things that could drop than that. So 257, what do you got? So why is whitespace NPP, for instance, still in here? Well, first of all, let me make sure I'm looking at the right thing. Okay. 7. So whitespace NPP, LU number, none of these got removed, and yet they are all doing basic thunks that could be removed. So this one is not doing a basic thunk, but the rest of these are all doing basic thunks that could get removed. So what's the deal? Yeah, not sure what that's about. So let's take a quick look at that loop that's trying to skip past thunk states. Right? So here we go. Don't care about you. Alright, all of my states should now be marked as optimized in case they weren't already. Now I look at all of these, and I want to see which state I'm looking at so that I can look for whitespace PP thing, or NPP, or whatever it's called. So looking at the pretty name, there's whitespace. Here's whitespace NPP. So how many transitions does it have? 1. Contains consume false. Does not contain a consume, so it's not optimized in. Okay, so the state called whitespace NPP is now marked as being optimized out. So now I want to come down here, looking at all the states again. This time I want to see someone who I know transitions to whitespace NPP, whitespace, and ask them, why are you not optimizing that out? So state, the state is optimized in. Looking at each transition, one of you, I know one of you transitions to the whitespace NPP. So I want to look at the pretty names we're transitioning to. Okay, the first one, you transition to whitespace. Well, that can't be right. Oh. Answer questioned. Wait, question answered. Rather. Copy pasted this thing again, which is not actually iterating the transitions properly. Hey, now we're down to 69 states. And so there should only be two places, I think, where I can find a 257. One of them is right here where it actually does a consume, so we're not treating that as a thunkable right now, because it does an action that we would have to do a considerable amount of work to maintain its behavior. And in fact, just to show you just how complicated that is, raw string finished lm, I don't even think we could optimize this out by doing the peak optimization, because if you look here, finished lm. Okay, so actually it looks like, yeah, it looks like this, if we did a peak optimization on this, it would pull that forward, and then this would get removed, because this consume would move up here, and this raw string find close would be pulled up here, so it would pull those forward, and then no one would transition to this state anymore, and so that one could get removed by a peak optimizer. Now, maybe what's worth it is to do a lightweight peak optimizer no matter what, right? So maybe we want to, on the next episode, write a peak optimizer that would optimize out something like this. Now, a full-fledged peak optimizer would have to do pretty heavy-duty stuff, and that's why we wrote all that set manipulation code before. It was to support the possibility that we want to do that, but it also just lets us correctly manipulate the states for things like the conditions out of fallbacks and stuff, so that we can find out for sure what set of states should trigger any particular fallback and just turn the fallback into any other type of condition, right? And that's been nice to have. It caused some bugs just being able to look at the state machine more literally like that, right? But what we could do is, instead of using that system heavily, what we could do is just say, keep sort of a track of how complicated things are getting, right? Like, sort of implement a portion of the algorithm that would do the right thing, to do a peak optimization, and then give it a tunable parameter that lets us say, hey, I don't actually want you to pull forward all of the stuff ever that you could possibly pull forward. Just look and see, like, if you have to pull forward more than one thing, then don't do it. But if you don't have to do any splitting, then there's sort of a lightweight peak that could be done, like in this case, where it's like, hey, I'm doing this as my input, and I transition to, like, I don't consume it and I transition to this, okay? And we look at that thing and then it goes, oh, you know what? That thing is actually fully a subset of this case handler here, so we would pull forward just this one thing and we wouldn't have to split this transition into multiple transitions, so it's simple enough to do like a simple peak optimization and pull that forward, and that would probably let us shrink down a couple of states where that kind of thing is happening, probably. Like, it would probably let us shrink down several of the roots to the operator substate machines. It would let us get rid of this one particular one that we're looking at here, and who knows what else we get rid of. It wouldn't let us, for instance, skip going to the root without consuming in a lot of cases, so there'd be a lot of go to roots that don't have a consume before them, because almost anything that wants to transition to the root actually doesn't want to have to look at all the subhandler things that it could do. For instance, you know, if we're looking at like a fallback that's like got 240 possible characters that triggers it, and then it's like, I fall back by not consuming what I saw and going to the root, well, that 240 characters isn't going to fit nicely into anything that the root does. So the only way to pull those things forward would be to start splitting the transition for that fallback into separate transitions, and then pulling forward the different things, right? But some of this you could do. Another thing we could do is to simplify transitions by merging transitions that have same behaviors. So this was something I was thinking about after I said this stuff up here about, oh, what if we check to see if all the transitions have the same effect, and if they do, it's a thunk state. Well, maybe the opposite of that, or a better version of that, is if there's a state with multiple transitions that do the same thing, let's merge them, because there's no reason anymore for us to leave them separate. The set system we have will let us manipulate them by unioning them together, so we can just say, for every transition that matches the effects of this transition in this state, merge its conditions into mine after we've done the simplification pass by unioning them, and then discard the ones that come after, right? We would need to be kind of careful that changing the order wouldn't I don't think the changing the order would make any difference though, because we've already done the work of simplifying the transitions in such a way that they are non-overlapping condition sets, so that order doesn't matter anymore. So we could actually just do that. We could just simplify them all the way down so that every transition that is a different transition in a state is guaranteed to have a different effect. And then this to-do goes away. And then we have a better chance of, when we're looking at a particular transition, being able to, when we look at its destination, find out that, hey, this particular, thing you were concerned about fits entirely within that transition over there, because it used to be as separate 3 transitions that all had the same effect, and now it's one big one. So that might make it the lightweight peaker a little more powerful, although it might also be a detriment, because now the transitions that are looking ahead might be bigger than they used to be too, so who's to say? But it would be a cool way to fix that. So that's a cool thing we could do, is merging transitions after simplifying them, merging identical ones. But I want to finish up today by looking at, here's the other case where our 257 shows up on the output now, which is when we're doing this del and match thing. And I think that this actually needs to change too. I don't think this needs to have 2 transitions, and the real reason isn't that this is like somehow like thunkable or something. It's that if we have a del and match, that's a very specific behavior that I want to hand code basically what it does. And the fact that there's a second handler here was really just a way for me to give a second transition destination. So basically what I should really do is just say that this is a particular case handler that has some hand-coded logic in it and actually requires 2 different destination possibilities, and just live with that as a thing that it can do, right? I think that would model this better, because what I'm doing right now, this 257 isn't actually true. This doesn't catch. This is not all possibilities. There are some of this will catch characters, but which characters it catches changes depending on the hand-coded logic. And then this is like a fallback that, when I originally was just putting things in, I called it fallback because it's like, hey, this is the thing that happens if the del and match fails. But now it says that it's the transition handler that matches all possibilities, and that's actually just doesn't make any sense anymore. So I think retyping the way this is structured internally would be nice. So maybe getting a type check in here sooner or later so that this gets eliminated and this gets merged as the on fail go to this or something like that, right? So that's that's got to happen. And like I said, I think we can get rid of both of these. This is more of a nonsense thing. This has nothing to do with optimization, and it's more about representation. This I think we can optimize out by doing a lightweight peak handler, which we'll do next time. Okay, so that's been this episode. We're now down to 69 states after optimizing out all of the thunkable states, and that's pretty cool, because if you compare that to where we were, bloop, that means that we've been able to shrink it by 7. 7 states got removed from the state machine, just by saying let's pull those things forward. One last thing I want to do is I want to look at something that I know used to be doing that. So let's go to the state for white space and take a look at this, and you'll see what happened now is this used to go to the white space NPP, and then white space NPP would always transition back to this without doing anything else, right? So this consume was, I think, already there, and the set flag was the unique part, and that set flag is now being pulled forward. So if I come up here, I'll bet we can find, yeah, so go to white space now. So what used to happen is it said set flag here, because that set flag came from the state for white space NPP. White space NPP was a state, and when we pulled forward the actions off of the lists that were for state entry, we pulled them into these bots. Now we've optimized out the NPP entirely, so now we have this cool thing that's happening where whenever in the modeling code I say transition to whitespace NPP, what I'm really saying is transition to whitespace, but first set these 2 flags, right? And that's sort of like a cool shorthand that the optimizer turns my model into a different thing that more exactly represents what I meant, but I didn't have to write out all those details. It could figure that out by understanding the shorthands that I'm using, right? So that's really cool. This is pretty exciting. All right, so that's this episode. Next episode will be all about that. Let's see. We did this. I want to try to at this point merge, well, it's like right here, I want to try to merge similar transitions with same effects. And really we should probably apply that before we do this, because there might be more thunkable states after you do that merge, right? And then after we do the skip past thunk states, we might want to do that a second time here. This starts to become one of those things where it's like what optimizations you apply shrinks the system down and might reveal redundancies that used to be hidden. So after doing this, some transition states might now look identical to other transition states that used to look different, and so there's maybe an argument you want to do that, or do all of these in a loop over and over again until you no longer find any more. But we're not going to do any of that yet. What we're going to start with is just doing this here, and then later, maybe hopefully in the next episode, doing simple peak optimization rather than this fully complicated one. Once we've done both of those, we'll be done with the sort of simplifying the model down, and we'll start looking at generating code. So hopefully 1, maybe 2 more episodes on this stuff. This has been an episode. I forget the number we're on now. Who even knows? See you guys next time. I'll have to look up the number before I record it so that I can give you the right number. Bye.